Maybe before you get too entrenched, you could just explain how the whole thing's going to go. I assume there's going to be the thesis thing, and then there'll be some open questions. Is there a sort of closed questioning section afterwards with the committee?
Yes, so the presentation is going to go, I think it's about like 45 minutes. And then we'll open up to questions probably for people in the audience first, and then moving on to Zoom to people have questions there. After we've addressed the general questions, the committee will have a closed meeting to address any other concerns, questions, comments. You're welcome to pose questions in the general questioning, but not obviously like a bunch, just a couple if you want to or want them addressed with everyone.
Okay.
So that's how it should work.
Cool, perfect. Should I be getting sound?
You can hear the audience talking, so I was just muting it until.
Oh, okay, cool.
They talking to you guys, just because it's a lot of excess conversation.
Yeah, no worries. Cool.
One more.
Oh, wait.
Waiting room.
Sophia, can you turn this point forward, try and then edit people for me? We have all of our speaking.
Yes, definitely.
Okay, perfect, thank you.
Ready to roll?
Gang's all here.
Awesome. Hi, everybody. Afternoon. Welcome everybody online. Thanks everyone for showing up for Nicole Krampitz's thesis defense. Entitled Demographic Impacts of the Most Severe Coral Disease Outbreak Affecting the Caribbean. Nicole came to us from University of Miami. Previous to that, she grew up in Dallas, Texas. She studied marine biology and minored in math and French, we were just talking about. And where she did at University of Miami, she also did research on coral classification in the lab of science. That's pretty cool. Since she's been here, she is currently a research assistant in my lab, and she's been a grader for the first year Mmes students. She's done a great job at that. I'm sure they all appreciate that. And she's also doing part-time work with NOAA right now in the NCREP program. It's pretty cool. And then after this, assuming she successfully becomes a thesis, she's going to work in a territorial coral modeling program. Nicole, thank you.
Thanks, Tyler. And thank you guys all for being here today, whether it be in person on Zoom. And so without further ado, we'll start. We're going to start really broad with what is a coral reef and why are they important. So coral reefs are often referred to as the rainforests of the ocean. And coral reefs are important because they create structure via our stony corals as pictured here. And these ecosystems are one of the most biodiverse ecosystems on the planet. So while they only occupy less than 1% of the ocean floor, they're responsible for housing more than 25% of marine life. So their diversity and their ability to create structure is really important to both marine life, but also to us as humans, because more than 500 million people rely on coral reefs for the indirect or direct ecosystem services these provide. So that would be things like food. People rely on coral reefs for source of fishing, particularly in island environments. Coastal protection, coral reefs can protect against high storm surges. In addition, a lot of people rely on coral reefs directly as a source of income. It's estimated that coral reefs bring in tens of billions of dollars a year for people, particularly in the tourism environment. Unfortunately, despite all of these benefits that coral reefs provide to both us and to people, they're facing a lot of different stressors that threaten their persistence. So examples of those stressors could be more local things like pollution, runoff, and sedimentation, but they can also be more global things that mostly have to do with climate, like coral bleaching, ocean acidification, and coral disease. Now here in the Caribbean, we've been experiencing really strong declines of coral coverage in the past few decades, and one of the biggest reasons for that is coral disease. Now, while the Caribbean makes up less than 8% of the coral's coral reef by area, it accounts for more than 2/3 of the reports of coral disease. And so for this reason, because it's a small area and there's lots of disease, it has been appropriately named a hotspot for disease. And indeed, there have been many disease outbreaks in the past 50 years, most notably in the 1970s. We had a white band disease that came through and decimated our lovely acroporid populations to more than 90% of what they once were. More recently and more locally, there was also a white plague event that happened in UNCI in the mid-2000s, and that took down our reefs to about 50% in some sites of what they once were. Now today we're going to be talking about a different and new disease, and that one is called stony coral tissue loss disease, or SCTLD or SCTLD. This disease was first reported in 2014 off of Virginia Key in Miami, and has since then spread around the Florida Keys and the Caribbean and decimated coral reefs in its path. Some populations of certain species have been reduced to less than 3% of their original densities, and many sites noticed coverage reductions of around 50%. Now, there are many reasons why this particular disease is likely the most lethal coral disease reported to date. One of those is that it has a very generalist nature. So it affects around 24 different species of stony corals, which accounts for about half of the species that we see in the Caribbean. Additionally, it has a really high prevalence on reefs. So while some reefs may have a background rate of around 5% of coral disease, so at any given point, around 5% of the coral there will show signs of disease, Prevalence for this disease can be as high as 60 or 70% for some of our highly susceptible species. It's also a highly contagious disease, and it's been transmitted really far everywhere. And it's been spreading quickly, and we've been unable to contain its spread. What might be really most concerning about this disease is the fact that it's been persisting. So it hasn't disappeared, and even in Florida in 2014, when they first noticed signs of the disease, they're still seeing new lesions on corals. Tissue loss associated with this disease also is very quick and severe, and most of the time leads to total quality mortality. So this is 8-time series point of corals, a couple billion atons in the USDI. And you'll see here that this very large colony, the dive weight per scale, disappeared within a matter of weeks. So in the very beginning there, we have disease lesions. This is pretty typical of something called tissue loss disease, where we have lesions that start in the middle of the colony and grow outwards. And that white part, those lesions have completely taken over the colony in a matter of weeks. We also don't know much, or we can't really tell what's exactly causing this disease. There's been a lot of studies done, but it's really, really hard, especially in coral diseases, to target the exact driver of that disease. What we do know is that it's likely viral in nature, and that it targets the endosymbionts and perhaps disrupts the zooxanthellae host relationship. And for those people who are not coral nerds that don't really know what that means, I'll try to break it down and say that a coral is an animal like you or me, has tissue, has a skeleton, but corals have a symbiotic relationship with zooxanthellae, symbionts, pieces of algae, and those live within the coral tissue, photosynthesize, and they give the coral a lot of energy. So it's suspected that this disease targets that symbiotic relationship and disrupts it. Additionally, we know that you can apply antibacterial paste to stop lesion spread, but that does not stop the chance of the coral getting new lesions and becoming infected again. That just stops the spread of that particular lesion. We also know that this disease is flowing and spreading through different water columns. So we know that it can do that or through direct contact, and suspected too that it's also traveling via ballast water from ships. And we know this because we've seen so many coral tissue loss disease up north, so in Florida and Florida Keys, and also down here in the Virgin Islands, but there's points where it was not found in between. So there are discontinuous dispersion patterns that were likely a cause of this ballast water transporting diseased water from one place to another. And this is likely, yeah.
Can you please share your screen on Zoom? Sorry about that. I just realized we're not seeing it on Zoom.
Okay. Yeah. Ink screen too. Okay.
I was wondering why my eyes were straining.
Can you? Sorry.
It popped up. It's just not. It was there. It was just not in presentation mode.
Just.
If you do that, the same thing that you just did, but
Yeah,
then
now.
there we go. Perfect.
This here. All right, so I'm missing that, and we're right here. Okay.
Thank you.
Yeah, sorry about that. I didn't realize it wasn't going through. So we think that it's going through ballast water, and that's likely how it came to St. Thomas. So the disease was first noted in 2019 in Flat Key, that little red star right there, and has since begun to spread across St. Thomas and eastward to St. John, eventually reaching the BVIs in St. Croix as well. At this point, this disease is fully found within the Virgin Islands, and it has already been really high prevalence on our reefs. We've seen a lot of dead and dying corals as a result of this disease. Now, bringing this back to my study and what I was doing, I was looking at the demographic impacts of stony coral tissue loss disease. So what is a demographic analysis? Well, starting with the baseline demography, which refers to the study of the characteristics of a population, a demographic analysis provides a mathematical description of how these characteristics change over time. So it'll tell us any factors that might influence statistical growth. And for a population such as you or me, a lot of times that means things like our population size, our age structure, dependently, and other metrics. For corals, they're a little bit different just based on the way that they age and they grow. So today we'll be looking at size, class, structure, which will tell us a little bit about the age, size, and growth of the coral. as well as community composition, which is essentially the species distribution. The 3 corals selected for demographic analyses today were Orbicellas, Parietes astrides, and Pseudoastria species. We're going to hear me refer to these a lot more throughout the presentation, so pay attention. But starting with Orbicella species, these are going to be our large, slow-growing mounding corals. They're the dominant reef builders, particularly in our deeper reefs here in St. Thomas. Contrary to that, we have Parietes astrides, and we consider this more of a weedy coral. It has really fast growth, and they pop up everywhere. There's very high recruitment, but there's a lot of high turnover too, and they don't contribute as much to the complexity and structure of the reef. In between that, we have our Pseudoastria species, which has traits of both of these species. They build mostly small colonies, but sometimes Pseudoastria will create larger or mounding colonies. Additionally, they have intermediate growth and intermediate susceptibility to stony crawl tissue loss disease. Forgot to mention that Parietes astrides has very little susceptibility to the disease, while Orbicella is also mildly susceptible to stony crawl tissue loss disease. Now, from these different corals, I created some hypotheses that I wanted to look at, knowing what we know about this disease. The first is that I thought that Parietes astrides would have higher population growth rates than Pseudoastria and Orbicella species. And this is simply because we know that that coral is more of a weedy species, and we know that the other 2 species have been facing some declines following stony coral tissue loss disease. So I figured that overall population growth rates would be higher in our Parietes astrides. Even though I thought they'd be higher in our Parietes astrides, I still thought that all population growth rates at all depths would be declining. So we wouldn't be having growing stable populations, they would be declining. And furthermore, decline in our corals isn't necessarily something that's new, sadly. But I thought that they would be declining at a rate that is faster than that during a time when we didn't have this disease outbreak, during a period of what we like to call no disturbance. Lastly, looking more at disease and patterns of disease, I thought that disease prevalence would be higher in our deeper reefs, as would be tissue loss over the course of the study. And there are a couple of reasons why I hypothesized that this would occur. One of which is that we have really high densities of Orbicella corals in our offshore and our mesophotic reefs. And previous research has shown that higher density corals, particularly susceptible corals, will increase disease prevalence. Furthermore, previous studies here have shown that white plague, a different disease, had higher prevalence at deeper reefs. And other studies in Florida have anecdotally showed that in our offshore reefs, they had higher disease prevalence than nearshore reefs. So moving on to our methods. How did I do this? Well, I used 12 different sites across St. Thomas and St. John. These sites are all a part of our territorial coral reef monitoring program, which for you guys that don't know, is a program that was established in 2002 and has 34 sites across the northern US Virgin Islands and St. Croix. At each of these sites, there's annual monitoring done for fish and coral populations to kind of see how they're changing through time. Now, these 12 sites were selected because they are the ones in which we have our demographic plots. And in addition to being spread around St. Thomas and St. John, they also have different factors to them. So we have 4 nearshore reefs, and these are going to be our corals that are nearshore and shallow. Additionally, we have some offshore reefs in our sites. So those are going to be further offshore and still somewhat shallow, but not as shallow as some of our nearshore reefs. And lastly, we have our 3 mesophotic sites, or our really deeper reefs. These are found right off the bank of St. Thomas and St. John, and they're really important because in the Virgin Islands, we're really lucky to have some extensive mesophotic reefs right around the upper limits of scuba diving depth levels, or lower limits, I should say. At each of these sites, demographic surveys were done annually. We chose to look at the study from 2018 to 2021 so that we could see what would happen after stony coral tissue loss disease. In addition to those 4 years, there was also a survey in 2020, the 2020 post-bleaching survey, to look at the effects of 2019 bleaching later on that. And that was done for all of TGRM. At each of these sites, 3 permanent transects were used in which a diver, like me pictured in this photo here, would swim along with a quadrat framer and take successive photos for the first 5 meters of that reef. And so the point of this is that we're able to take photos of the same corals from year after year after year and be able to phase track them and see what happens to them. So when we take these photos, we end up with something that kind of looks like this. A lot of algae, a lot of sand, but there are corals that we're able to ID. And like I said before, the point of doing that is that we want to phase track each of these colonies. So it's important to see on a colony level basis if each of the colonies are growing, if they're shrinking, if they're dying, if they're undergoing fission, which is when two corals will separate into, or one coral will separate into two, mostly due to partial mortality, or fusion, where two corals will come together as one. For this, we were also able to determine the change in tissue area over the course of the study. And so you'll hear me refer to that a lot as tissue loss, simply because most of our tissues did lose corals, but it really is just a change in tissue area over the course of the study. Now, moving forward, what we did with that, or in order to do that, it took 3 simple steps. The first of which was to ID every coral in the framers, let ID what species it is, and give it a unique ID name. The second was to follow it through each of the successive years. So to identify each of the colony again, see if it is bleached, if it died, if it's diseased, and so on and so forth. And to also see if any new recruits popped up in that plot. So for the purpose of this study, recruits are referred to as new corals that are entering the demographic population here. So at this point, they're not actually very small recruits, they are more juveniles, but they are new to the population that we see in the plots. The last step was to simply trace all of these corals so that we could get their different linear area. We end up with something that looks like this. We're able to track each of these corals over time and essentially see what happens to them to see their fate. Seems pretty easy, right? Well, if we do some math to see how long those simple 3 steps took, you'll see that each transect took about 45 minutes, whether it was to ID all of the corals or to follow each of the corals. At 3 transects per site, 12 sites per study, and 5 different years, that's about 135 hours of looking at your computer and following corals. Now, what that does not include is the 6,414 corals that I individually traced. So if we go back in and add 45 minutes to trace each of these transects as well, it took about 270 hours or more than 11 days just to follow those corals. And this kind of underscores a bit that while demographic analyses are really helpful and they provide a lot of different information for us, they're not done super often just because they are really tedious and time consuming. Now, once we have our corals and they are traced, the next step is to put them in size classes. So the area of each of these corals was put in bounds and put for size classes. So our smallest size class 1, went for our smallest corals, and so on and so forth. And what we end up there is data that kind of looks like this, where we have an ID for each of the corals, their area, and their given size class. And the purpose of this is that we're able to tell from year to year how the corals are transitioning, if they're moving up in size class size or down in size class size, to see what's happening to the population as a whole. From these, we can then create population projection matrices. And bear with me, guys, as we explain a little bit of math here. I'll try and make it as simple as possible. But the matrix is actually this part right here. And to orient you guys on how to look at it, this top row here is what we consider our state. So whether a coral is at size class 1, 2, 3, or 4 at the beginning of the year. The other column there is our fate. So what this coral is, what size class it's in at the end of the year. So you're looking at the transition from the state to the fate, and that's what each of those values are inside of that matrix. So if we look at all of those values on the diagonal, they're going to be the probability that a coral will stay in the same size class at the next year. So for instance, the probability of retention for a size class 1 coral would be around 49% in this particular matrix. Anything below that diagonal is going to represent growth. This is what we want to see in the corals. This is what we want for a really happy population. Unfortunately, we don't all of the time, but that is going to be our growth. Anything above that diagonal represents shrinkage or partial mortality. So that would be a coral of a larger size class going down to a smaller size class. We did have this a lot in our transects just because of stony coral tissue loss disease, a lot of disease coming in and reducing corals via partial mortality. Through these matrices, you can also tell the probability of death. And I just have to point out here, this matrix is actually one of the ones that we had in our studies. And the rate of death really highly changed based on size classes. So our larger size classes had lower death rates than our smaller size classes, which is not something that's new in the coral world, but it is important to point out. And using these matrices, we're also able to determine population growth as a whole. So we can take this matrix, which I'll remind you guys is this part right here, and we're able to find the solution of it through some math. And that solution is a value also known as our eigenvalue or our lambda, and it will tell you whether our population is growing. If that specific value is above 1, our population is growing. If it's at 1, our population is stable. And if it's below 1, our population is declining. Now, these growth rates allow us to predict future scenarios by projecting that growth rate on the current population to see how that population would fare in, say, 10, 20, 30 years if conditions were to remain the exact same that they are now. Into our results. So what I found, first off, found that our percent coverage dropped in our demographic plots over the course of the study. So on this y-axis, we have percent coverage of our coral, average percent coverage in site, and on the bottom, we have our sample year. Reminder that 2020 post-bleaching is that post-bleaching census that occurred in early 2020. We saw a significant decline in our percent coverage over the course of actually 3 years, by 2018 to 2020. And if we break that down by species, we'll see that a lot of that was driven by a similar decline in our Orbicella species. So these are the top 5 species in terms of percent cover that we saw over the sites. Looking at that and breaking it down by reef type, we'll see that there were differences between our nearshore, offshore, and mesophotic reefs. So our nearshore reefs did decline in percent coverage, but there was not a significant decline. And additionally, after 2019, they didn't really seem to decline much further. Offshore reefs, on the other hand, started at around the same percent coverage for these demographic plots as nearshore, but they declined significantly over the course of the study, dropping about 7% in coverage. This was mirrored in our Orbicellas for our offshore, that green line right there. And the same held true for our mesophotic sites. Now, our mesophotic sites had the highest percent coverage to start with, and they also dropped the furthest. So we lost about 11.5%, or a relative percent drop of around 45%. And that was also similarly driven by a loss of our dominant reef-building Orbicella species. Moving into tissue loss, so what we saw on the individual colony basis, tissue loss was in this particular study looked at as how much the difference in tissue area between the last year of the study, 2021, and the first year, 2018. Absolute tissue loss refers to how much actual area was lost between the studies. So if I said absolute tissue loss of 50 centimeters, that just means an area of 50 centimeters was lost. Relative tissue loss is the percentage of that by how big the coral was to start with. So if the coral was 100 centimeters to start with and it lost 50 centimeters, that means it had a tissue loss, relative tissue loss of 50%. Overall, all species and corals combined, there was a relative tissue loss of 20% seen for our corals. And in fact, only one species, Krampitz asteroides, was the only one to see consistent growth when split out by species. So this was particularly true in our nearshore environments, especially Fish Bay and Coral Bay. We had a lot of growth of our Krampitz asteroides. Breaking that down by site, we saw that tissue loss increased with increasing distance from shore, both in absolute and relative terms. So mesophotic reefs had a significantly higher absolute tissue loss over the course of the study, which isn't too surprising given how big those corals are. But both offshore and mesophotic reefs also had a significantly higher relative tissue loss than our shallower reefs. Looking at disease prevalence, we'll see that that also was kind of mirrored, where we had a higher disease prevalence in our mesophotic reefs than we did in our shallow reefs. It was almost 3.5 times higher. So bringing that back to our hypotheses and what we wanted to look at, I thought that disease prevalence and tissue loss would increase with increasing depth. And from these results, we can say that yes, it does. Moving on to our species-specific impacts, coral mortality varied highly by species. This isn't surprising given what we know about the susceptibility of different corals to sodium coral tissue loss disease. We did have the disappearance of 4 species from our demographic plots completely. So that would be the ones you guys see below: Pseudodiploria cliposa, Dendrogyra cylindris, Phagosine associ, and Diploria labriformis. So a quick RIP to those corals. We also saw really high mortality rates for Meandrina meandrites and Pseudodiploria extravosa. Those are around 90%, and around 70% mortality rates for Copephilia nasons and Montastria cavernosa. Now, with the decline of a lot of these gray corals and a lot of our bouldering species, we also saw a slight shift in relative dominance of our particular species. So we went away from a lot of these types of corals to, as you guys probably guessed, a dominance of Krampitz asteroides. And this is really important because in a reef, if you're going away from these big bouldering corals that create structure and places for fish and stuff to hide, towards these Krampitz asteroides, which are really normally small species that don't contribute as much to the reef. Not only are you lowering your species diversity, and you're going from a lot to only one species, but you're also reducing the structural complexity of the reef. And that's really important because the structural complexity of the reef is one of the biggest things that contribute to, they're how that reef contributes to us as humans and as marine life. It's able to be storm structure, it's able to have little places for fish to hide in and to live in. So if you're reducing the structural complexity, you're also reducing the potential of reefs to provide ecological benefits to you and me. Moving on to our last part with our growth rates. To orient you guys to this graph, on our y-axis, we have our dominant eigenvalue, our lambda, our growth rates, our population growth rates. On the x-axis, we have our transition years or time, and these are split up by our 3 different species. So right off the bat, you guys can see that all of these values are below 1, which indicates that all of our populations, regardless of species, were declining for these 4 years of the study. Now, Krampitz asteroides did have higher growth rates than our other 2 corals, and this wasn't super surprising given what we know about its weedy nature and also its susceptibility to stony coral tissue loss disease. After that, we had Orbicellads, which started off lower, which kind of grew a bit, compared to our Pseudoasteroid species, which kind of showed a little bit of decline actually in the further years of our study. Bringing us back to our hypotheses, I thought that Krampitz asteroides would have higher growth rates for our populations than Orbicella and Pseudoastrea, and that was indeed correct. I also thought that growth rates of all depths would be declining, which we did see here, and that they would be lower than those previously estimated during a time of no disturbance. Now, the study was not able to do that on its own since we didn't have the pre-data, but we were able to combine with data from a previous Mmes student, Alexander Gutting. She's on my committee. She's been super helpful with everything, but she looked at Orbicella and Pseudoastrea at these same sites during the time frame of 2014 to 2018 to examine times of no disturbance and hurricanes on growth rates. So by using her data and mine together, we're able to compare what happened before the disease outbreak and what happened afterwards. Now we're missing data, as you guys probably could tell from our near-shore Orbicellads. That's simply because there wasn't enough Orbicella in Alex's data in order to make transition matrices. It requires a lot of replicates. And similarly, there aren't enough Pseudoastreas in our mesophotic environments for this either. They're just not really deep dwelling corals. They're more shallow water corals. But from what we can tell where we have the pre and post, we see that for Pseudoastreas, there definitely was decline following the introduction of stony coral tissue loss disease. So beforehand, values were a little bit variable. I'd like to point out that this particular one here is likely caused by the hurricanes, the 2 hurricanes actually, that came through St. Thomas and St. John in 2017 and kind of ripped apart a lot of near-shore corals. But even disregarding that, or even regarding that, we can see that Pseudoastrea growth rate populations decline, particularly in our near-shore environments. Orbicellads did the same, looking at our offshore and mesophotic environments, and they declined pretty sharply following the introduction of stony coral tissue loss disease. You'll see also that before this disease, these corals actually had population stability. Their lambdas were right at 1 for some years, which shows that these corals at certain times previously during no disturbance were actually in stable populations, and after this disease, they have significantly declined. Looking at different reef type comparisons, in general, we'll see that offshore reefs definitely declined the most for both of our species, but following that decline, both Orbicella and Pseudoastrea reefs shot back up a fair amount. Mesophotic reefs, on the other hand, had a sharp decline in Orbicellads, but their recovery is a little bit slower and it's not nearly as upturned as our offshore reefs. Bringing us back to the hypotheses, I thought that growth rates of all depths would be declining and lower than those previously estimated during a time of no disturbance, and we did find that to be true. The last thing we did with these growth rates is we took them and were able to model them forward. So taking the different growth rates and applying it to the population that we have right now, we're able to see what would happen if environmental conditions would stay the exact same. So I should note that these projections assume the exact same environments, and there's a lot of things that could happen between now and then. We could have additional disturbances come in and decline populations further. We could have stabilization of growth rates after the disease or recruitment events, and all of these things would change these models. But just using the growth rates that we have now and the populations that we have now, orient you guys to this axis. The y-axis is the number of colonies. That's just from these 12 sites, how many colonies there are. And the y is years. So these are all projected out for 30 years. Each of the colors represent the size classes and how many corals are in each of the size classes. So we'll see for varieties as geoides, that there was decline, and 30 years out, populations were reduced to about 60% of what they are now. For Ocellas, it was a lot sharper decline, and in about 20 years, populations were reduced to 15% of what they are now. Lastly, we had Pseudoastrea species, which declined even further than our Orbicellas, and this wasn't surprising given what we had seen about their growth rates continuing to decline. But you'll notice you can tell differences with these as well about what size classes are contributing to that decline. So for our Pseudoastreas, we have actually a very large number of size class 4, and they were able to stay pretty high throughout the entire population, despite declining growth rates. All right, moving on to a quick summary of what this all means and why it's important. Key points is that species diversity was lowered over the course of this study. And so we had a transition from a lot of really important mounding dominant reef builders into a lot more of our weedy corals. Additionally, we saw that disease was highest in mesophotic reefs, disease prevalence at least, and tissue loss was also highest in our mesophotic reefs. This was an important note of the study because not many studies have classified the nearshore to mesophotic reef gradients with this particular disease. And it's also important because our mesophotic reefs here have really high coverage, and they're sheltered from a lot of nearshore stressors that the coral reefs there face, such as runoff, pollution, and sedimentation. So it's really important to see what is happening to these reefs here in order to tell what's also happening to our reefs further than those that we can reach. Additionally, we saw declining growth rates for all of our species. And furthermore than that, we saw that they hadn't rebounded back to previous populations from them beforehand. So it is likely that our populations are still continuing to decline, even if we don't see them actively having disease. This also brings us into the question of how long we're going to be seeing the impacts of these diseases. So I think that the full impacts of it have yet to be realized, given what we've seen in Florida and given what we know about how long we can have lasting impacts, which brings into the question of recovery for those species. So we did have, like I said, declining growth rates for all of our species, but there was an upward trend for our Orbicellas and our Pseudoastreas in some environments, which means that it may be possible for them, given a few years, to come back up to more steady growth rates and stabilize as a population. These declining growth rates, though, were probably most concerning in mesophotic reefs, just because of how little they were able to recover from what we've seen and from what we know about mesophotic reefs, which is their very low light levels. The corals there often have lower growth rates, lower recruitment, and recently it's also being shown lower lesion recovery rates. So recovery in these reefs is likely to be more prolonged than our other reefs and pretty poor. Additionally, there might be other different factors that come into play outside of just corals and disease. And so examples of that would be positive feedback loops with the environment. So an example of that is as corals die, algae and sponge overgrow those dead coral skeletons. And that not only reduces the amount of availability on the reef for new coral recruits to settle, but it also increases the likelihood of that new algae and sponge directly interacting with live coral. And it becomes more of a space for competition and so on and so forth. Another sublethal impact is the fact that a lot of our larger size class corals died during this disease event, and those are going to be most of your sexually mature corals. And so if you're removing a lot of sexually mature individuals from the environment, whether it be through full mortality or partial mortality, you're going to also be removing or lowering the number of recruits in the next year and then lowering the contribution to the population. Additionally, even if coral did survive from the disease, It probably put a lot of energy into fighting that disease, and it now has to think about regrowing that skeleton and going for tissue regrowth. And so it has less energy to focus on reproduction and stuff like that. So it might also make it more susceptible to other stressors. So those are a bunch of things to think about. Despite all of these negative outlooks for our corals, I do still think that there is hope. This disease will at some point become endemic if it isn't already. And as the corals that are susceptible to this disease die off and the different genotypes that are too, we're going to be left with corals that are more resilient and are not going to be dying from this disease. And hopefully if those corals are able to stabilize, then we can move towards population growth and just retaining the corals that we have and seeing them on our beautiful reefs. Additionally, we didn't see a lot of recruitment, particularly for our orbicella species, and some of these species are known to have false recruitments, not yearly recruitment. So it's possible that we just didn't see the recruitment in this study, and that in future years there may be more recruits which could contribute to the population and help further growth. Moving on to our different management, there have been countless different management actions applied for this disease. They've actually been really great here in the Virgin Islands when it comes to applying the antibiotics, like just looking at different monitoring of this disease. They're even working on probiotics in certain places. So I'm not going to go over what can be done for this disease because we already are doing a lot of it, but I will go over directly what we saw from this study. And that was that our ovicellas were declining, even though there are dominant refilling species, particularly in our projection growth rates. But with those particular projections, if you were to add small size class corals into those projections, it really helped with the stability of the populations and even growth later on. So if we were to add more of our smaller ovicellas to the environment, particularly in offshore environments, just because we notice those drop so much more than our nearshore, perhaps we could help to stabilize these populations. So I know that we do a lot of acroprid different outplanting here, but maybe put some more little orbicella babies back on the reefs too. Additionally, we also saw that our death rates for the Pseudoastrias really changed based on their size. So the size class ones had much higher, much lower survival rates than size class 2. So if we're to consider also expanding to Pseudoastria restoration, I would highly recommend waiting until colonies are at least 4 centimeters squared to put them back on the reefs, because that really seemed to increase their chance for survival. Lastly, and this one's a little bit more theoretical, but we did see that those growth rates, even 3 years out, haven't properly recovered following this disease. So in order to truly figure out what's happening or to help them recover, we need to figure out what's impairing their growth. So why haven't they recovered and what's inhibiting them? And that could be a variety of things. It's a really difficult question to ask. But if we're looking into future management and future intervention, I think that's something that should be further researched, whether that be able to be directly or take out one factor at a time to see what's happening. So thank you, everyone that's been able to help make this research come true, particularly my advisor, Dr. Tyler Smith, and my committee, Dr. Pete Edmonds, Dr. Marilyn Brandt, Scotting. Thank you to my funding source, Lana Vento Charitable Trust Fund, as well as my family and friends for their support. So Razi for her help in TCREP data, Sarah and Tasha for their help in R, Aaron for edits, and Lindsay, Andrew, and other members of the Mmes cohort for their support, as well as my parents and Pat for their support. And last but not least, we have Charlie for her anxiety reducing hugs. And thank you guys. I will now take questions.
Is in terms of your size categorizations, what were your thresholds for the bin sizes, and then how did you determine your bin thresholds?
Great question. So the threshold for the bin sizes changed based on each of the coral species and their potential growth. And it had to do with both how many corals we had and so like we could do more bins for the corals that we had more of. For Orbicella and Cinerastria, do you want the actual numbers or?
No.
No, for Orbicella and Cinerastria, I actually kept the same values that both Alex used, so we could keep it for comparison. And I think they're also really similar to what Edmund used, so there's a lot of comparison purposes. For Brady's Asteroides, those I actually created myself, and it had to do with the distribution of how many species we had in each of the size classes. So we had the most in our really small size classes, and that's not surprising. But the last thing that we wanted to do also is they weren't entirely even size bins. There was more definition in our smaller size classes, since smaller size classes are more prone to growth and stuff like that. So they started out kind of narrow and got larger.
Thank you.
Yeah. Catherine.
Great job, Nicole. So you finished on that the growth rate has been inhibited. It hasn't gotten back to what it needs to be.
Correct.
What is like an exciting or like a hypothesis of why you think that might be? Or like, where do you think exciting research should go?
Yeah, that's a good question. So I will say that this study ended in 2001, so we don't have the most recent of years. And so I'd say, especially in our mesophotographs, there might actually still be disease that's inhibiting them. Like we are seeing active lesions. I think a lot of the reason is probably time. I think even if those that have survived, they're still working on growing and trying to recover from that. And additionally, we've noticed in our growth rates, they're most sensitive to retention of our largest size classes. So the biggest corals staying alive, essentially. And we didn't have that during times of disease, obviously, because a lot of them died. And you're not gonna have like a really small coral suddenly become like this big, huge coral. So I think a lot of it has to do with just dynamics of the populations. And to answer your question, I'm not really sure what the most interesting thing would be to look at. I think probably continuing the demographics and just looking at probably what's happening to those big size classes. And also if those big size classes are able to contribute more to the environment with the groups. So looking at the biggest one and the little new babies coming into the population.
There's some questions.
Do you wanna switch?
Yeah, we can go.
Sure. My question is, the Orbicellas, when it showed that like sharp increase in growth after the disease, was that corals that had, I guess, eaten stony coral started to grow again, or like where did that new growth come from? all of a sudden?
So the,
Actually, maybe repeat the question.
oh yeah, sorry. So Rachel asks, we saw a sharp incline of growth rates after stony coprolitic disease, primarily I assume you're in the offshore environments where they kind of like way back up. Where is that growth coming from and why does it look like that? So the important thing to remember about those graphs is that each transition year is independent from the year beforehand. So if in the year beforehand, let's say half of our population died, our growth rates are going to be really, really low. The next year, you're starting a population where half of them died last year, but that transition is independent. So for them, you have a fully healthy colony, like population that you're starting with. And so even if only a quarter of them die, your growth rates are going to go up just because you're not declining as much as the year before. So I don't know as much if we're looking at actual growth of those colonies. They're not growth rates of the individual corals, but I think as a whole, you're looking at more stable colonies or more stable populations where less of them are declining. So I think that's where that came from. So answer your question. Yeah. Okay. Awesome. Lindsay.
Yeah, that's great. Really interesting. I found it surprising, or I found it interesting that even the varieties corals were declining. And given that they're the least susceptible to skittle, do you think their populations are declining because of skittle, or were they other factors that you missed?
Yeah, so I think that I think it mostly has to do with varieties and strains as a whole. They have like really high turnover sometimes, so we just had a lot of colonies disappear, and that contributed to that. Previous studies have found varieties asteroides, even in Puerto Rico, to have way lower growth rates than we found here, so it's not uncommon. And that study was done during a time when there wasn't a disease outbreak, so I don't think that disease is driving that. I think if we took that value and split it up by different sites, we just see it's more of a situation of that. Now, I wish that we could do each of our sites individually, but unfortunately, they're not enough replicates of each of our corals to put them in all of the size classes to do that. But I don't think that it's mostly because of the disease. I think it's just because of the environmental stressors that our corals, even our super weedy ones, do still face. Yeah, Pete.
Hold on. Very cool. I love seeing such a huge quantity of data crunched there. You introduced your presentation by saying sort of Skittles decimated the reefs of the Virgin Islands, but really the reefs were not in a fantastic state when you actually started the study.
This is
So-
very true.
Can you sort of place your understanding of the disease in like the longer term perspective of where these reefs have come from and where they're going to?
Right, yeah, great point. So our reefs have been decimated here recently, so we're looking a lot at this point, I think, about relative tissue loss, so like how much we've lost compared to what we've had, because we're trying to cling on what little amount of coral that we have. If we're placing this in the context of essentially reefs 50 years ago, the amount of coral that were lost is not super large in comparison to what's been happening over the years. The fact that it's happened in such a short time span because of one stressor, one impact, I think is really important. So I don't exactly have numbers for how high Virgin Islands was when we first started, but I do think that in a short time frame, it's been really impactful to where we are right now. I have a follow-up question with that?
So in the big picture, is
Yeah.
Skittles worse than hurricanes, or is Skittles worse than bleaching?
I would say that I think hurricanes, based off, especially what Alex showed, is that they're gonna be a single stressor at one time point that really affects a lot of our nearshore reefs. And that stressor abates pretty quickly after the hurricane's done. I don't think that it has as many long-term effects as stony coral tissue loss disease. Bleaching, it depends whether you're looking at bleaching as a whole or bleaching and the after effects of bleaching too, like we had with the white plague. I think that this particular disease outbreak is probably more impactful than most of the bleaching that we've had. I can't speak for every single one because I don't know all of them. If you combine them all together, though, the stress of bleaching maybe over the series of 50 years may be a more impactful to these corals. But I think that if we're looking at a single event or single here in the Virgin Islands, that this disease has probably been affecting them more.
Cool, thank you.
That's how I see it. Aaron.
Hey, Nicole, great job. Really awesome presentation. I was just wondering if you know how your growth rates that you found relate to like across the Caribbean region or other areas?
Yeah, great question. So from what I was able to find, we didn't really have any comparison for our Siderastria species besides what we have for Alex's, and you guys showed that, or I showed you guys that already, that they did decline. But to start with, they weren't at stable or growing populations. For Orbicellus, there have been a few studies, most of them done by Pete, but some of them done in Culebra and Puerto Rico. And essentially what they've shown is that it's kind of site dependent. So in some places, Orbicella, particularly Orbicella annularis, is being the focal species. Growth rates are stable or even potentially growing a little bit. But then there are other sites where growth rates are really low, even during times of no disturbance. So it's kind of just dependent, like I know Pete has found that in Yawzy versus Tektite, they're like extremely different. But I think it's more site dependent and they are kind of along the lines of what we've seen. We've seen you combine them all together in surrounding areas of the Caribbean. Freddy's estuaries, I think I spoke a little bit to this, but I think in St. John, Pete found like pretty similar ranges where they were really high, almost stable or growing, just right along that range. But in Puerto Rico, a study about like 10 years ago showed that they're declining in those areas. So I think it really ranges based on areas and the stressors that those corals are perhaps introduced to, or perhaps even the genotypes of the corals that are there. So in short, yes, they do align. They're a little bit better than some places and they're worse than other places. So we're kind of right in the middle. But there are no disease growth rates available yet. I imagine people do though. Or will continue his, work. Any other questions? Continue, or you can comment also on that to Aaron.
Oh yeah, planning to keep doing more stuff, but your act will be hard to follow. So in terms of like where this is going to go in the future and the exciting work to be done, if you look at the technique you've applied and I think we talked about this when you visited Northridge. It seems that no matter how much time you spend underwater and how many corals you count, you never really have enough. And then when you look at your graphs with the lambda values and the error bars, or the confidence intervals overlap so massively that being able to detect a difference among times is very, very hard. So,
Yes.
is this the technique to move ahead, or do you see a new technique coming in, or how do you get those error bars smaller so you can test for differences over time?
Great point and question. I don't know exactly for looking at directly the growth rates, but I think a good application of this and something that I plan to do going forward is taking this from direct matrix projection models, so where you're putting your corals in size bins, and doing interval projection models, so where you're able to take each area kind of as it is. And I think from my understanding of it, that's able to fill in more of the gaps that we have here and reduce that error, because you're taking an interval over the whole area instead of just putting them in little bins. And I know that you can it takes less corals, so maybe moving forward towards that, but I'd like to also underscore that I still think that this work is really important, although it is very time consuming, just because of the intermetrics that it does tell you about corals and coral populations, and just because there are a lot of really large errors and maybe you're not able to say it's significantly declining and so on and so forth. I think it's still a lot more, it tells you a lot more than just looking at percent coverage, which is something that we normally do because it is, so much easier, simpler, and straightforward.
And I would interject too that I feel like so much of what you showed with the work that you're doing and how time consuming it is you sitting there tracing corals. I think with new machine learning technologies and things, there's lots of avenues to automate this. And I don't think the time underwater is even that expensive, but we can do robotics for that as well. But I think the real bottleneck is the processing of the images. And once you have that, like, you can automate that whole flow. Totally speed things up and allow you to add more.
I think we're also limited by just the number of corals that do exist regardless of, or just their population densities. So we can only do this for a few different species, and even in this study, pulling together our orbicells and our pterodastrids when we know that they are not the same species and they don't have the exact same growth rates and forms. Yeah, Rachel.
I have another question. This is kind of a general one. So like, because you spent so much time hand tracing like 6,000 corals, were there some that you saw over the time span that have just like done really well and they look really good that you think it even be interesting to do some kind of like histo study or like spawning or something with? Because like maybe these ones too are the genomes that are outlasting and resilient and resistant to whatever's going on. Did you see?
That's a great point. So to start with the first part of your question, yes, particularly when I was going through Fish Bay, like you learn some of the corals, at least their name and where they are and where they're supposed to be. And some of them had like crazy growth. I would be like, I don't know how you went from this size to this size. Like, I feel like I'm missing something here, because everything means it shouldn't be happening. And I didn't think about, like target signaling, taking out those corals, writing them down, and being like, we should be looking at like, what are the genetics of this? Like, why is it happening to this coral? That's an excellent point. If I were to do this work in the future, I think I definitely would make a note of them when I see that, because it happened mostly for varieties asteroides, but it did happen.
Thanks, everyone. I think we'll retire for private committee meeting. Thank you all for coming.